This is a short lecture, just performing another bivariate linear regression. I wanted to get another example up for you guys to walk through, and also this example will be a little bit different because we are using a categorical predictor, and we're going to talk about what the implications are of using categorical predictors. So I'm using the same homework data, which is the ICU data, but this time I'm sort of arbitrarily picking a different variable as the outcome. So I'm going to use the sequential organ failure assessment variable as the outcome variable. And what we're going to look at is the regression of gender on this variable. So SOFA is a continuously distributed variable, which is what's required for regression, a continuous outcome. But now we have a categorical predictor. So we'll talk in class this week about the general linear model and how regression and ANOVA are both part of or a model in the family of the general linear model. So these are sort of interchangeable analyses in some sense. But the thing here is because we've been dealing with linear regression using continuous predictors, and that makes sense. And we talked about the assumption of linearity of the relationship between the predictor and the outcome, which makes sense with two continuously distributed predictors, and or one continuously distributed predictor and a continuously distributed outcome. But the same can be said for a categorical predictor, that a categorical predictor can still have a linear relationship with a continuous outcome. So this gender variable is coded 0 and 1, where 0 are men and 1 are women. And you might think to yourself, well, if I have a continuously distributed outcome variable and a categorical or two-group predictor variable, why don't I do a t-test for the mean difference in the outcome, which certainly is a reasonable approach. So I did that here. You can see the descriptive statistics suggest that the SOFA score, where higher scores are worse, the SOFA score for men is 11.29 and for women it's 10.27, and the t-test is significant. So the obtained t here is 3.12 approximately, and that's a p-value less than 0.01. The mean difference between the groups, the subtraction between 11.29 and 10.27 is 1.015. And that test is significant. So let's look at the same thing in the regression context. So the first thing I did was a correlation between SOFA and gender using the regular dialog box for correlation. And you can see that it is significant, and the obtained R value is 0.134. So there's a linear relationship between R and T that's shown with the equation on the top right, such that any obtained R can be expressed as a between group difference t-test as the square root of t squared over t squared plus the degrees of freedom for the t-test. So I solved that problem here, showing the obtained t value from the previous slide of 3.12 and how it can be transformed into the obtained correlation coefficient, which is 0.134. Another thing that it's useful to note here is the meaning of correlation as increasing scores on X corresponding to, in this case, decreasing scores on Y, holds here as well. So I said that because the correlation coefficient is negative. So with two continuously distributed variables, this would mean as you increase along the x-axis, as scores get larger on the x-axis, scores tend to get lower on the y-axis. The same interpretation is true here. We only have two scores on the x-axis. We have a 0 representing the men and a 1 representing the women. And so that coefficient literally means as you move from 0 to 1, right, you increase along the x-axis, that is, as you move from men to women, or increase from 0 to 1, scores on the SOFA tend to go down, which is just another way of saying what we saw in the t-test, which is that women have a lower score than men. So as you move from men to women, or 0 to 1, scores tend to go down, reflected by a negative correlation coefficient. We can visualize the linearity of the relationship between gender and SOFA score with a scatter plot, just like we would with a continuous by continuous relationship. So shown here is the SOFA scores for sex or gender equals 0, and the same thing for gender equals 1. There's nothing in between because there are no scores in between. I wanted to point this out to you guys before, so I'll just say it here. If you double click inside the scatter plot, you have an option, and it's shown right up here. It says add fit line at total. So I just double clicked inside that scatter plot, clicked that option for adding the fit line, and it dropped the line in describing the relationship between gender and SOFA in this data. You can see the regression equation is actually given in the line, and there's an R squared value, so from that you could move back to the R value for this data. And here it is. So the regression of gender on SOFA, the regression equation is 11.29 minus 1.02 times the predictor X, which in this case is gender, and it can only take on values of 0 and 1. This relationship is linear. It does satisfy the assumption of linearity between the predictor and the outcome, which it always will, because with only 2 points on X, you can only fit a straight line. So this slide just shows that I performed this regression in the same way I normally would using the linear regression dialog boxes. What I'm showing here is just what's given under the statistics button. I'm not asking for anything special here because this is a bivariate or simple linear regression, but we will look at some of these other options when we do multiple regression. And here are the results. So there's a lot going on here. This is still just the regular linear regression output. I'm going to move from the top to the bottom and starting on the left. So the regression results show what the model was. Gender was entered as a predictor of the dependent variable SOFA. The next one is the model summary. So it shows the big R, 0.134. That is the correlation coefficient. When we do multiple regression, big R will become the multiple correlation coefficient. So it will be the percent of variance accounted for by all the variables in the model, not just, well, in this case we only have one, so it is equal to R. R square is there. Adjusted R square is going to be a complexity penalized R squared value, so it will still be the proportion of variance in the outcome explained by all the variables in the model, but it will be downgraded a little bit, penalized for complexity. Here we are estimating an additional parameter in the intercept that we wouldn't have been estimating in a simple correlation, so we are getting that complexity penalty. The standard error of the estimate is there, which is the average error of prediction. So when I go to predict SOFA, I can expect to be off 3.7 SOFA points per prediction. We talked about that value last time. The ANOVA dialog box gives the significance of the whole regression. So there's an F statistic, which is the ANOVA for the regression model as a whole, and its corresponding p-value. It has 1 and 528 degrees of freedom, which is the same as it was before, groups minus 1 in the numerator, and then n minus groups in the denominator. I wanted to point out what's in red in the middle of the slide here shows that in the two group case, t squared is equal to f. So 3.12 squared is 9.7. That's true as you move from a t-test to an ANOVA, and it's true here as you move from a t-test to the ANOVA describing the regression model, because ANOVA and regression, as I said, and the t-test are all interrelated, especially in the case where the predictor is categorical. If we had just run an ANOVA on this data, we would have gotten the same F value as we're getting here in the regression context. Up on the right is the coefficients box, and you guys know that the first row gives the significance of, well, the actual value of the intercept, its t ratio, and the significance of the t. So that tests the null hypothesis that the intercept value is equal to 0. In this case, it's 11.29. It's 11.29 SOFA points, and it describes, like any intercept, it describes the expected value of y when the predictor is set to 0. So this is, well, you guys know this is a categorical predictor where 0 describes men. So 11.29 is an interpretable coefficient here. We said before sometimes the intercept in a linear regression is not interpretable or not interesting. When you have a categorical predictor, it becomes interesting and interpretable because one of those groups is coded as a 0. So that coefficient, the intercept, describes the actual value of the outcome for the group coded as 0. And you know that the significance in the t-ratio for the slope of the predictor describes, as we said, the expected change in the outcome for every 1 unit change in the predictor. So with its corresponding t and corresponding significance value. On the next slide, we're going to interpret that coefficient. So as I said before, we're looking at the coefficients box up in the right now. Because the intercept now represents the expected value of y when x equals 0, which in the case of a categorical predictor corresponds to the expected mean on the outcome for the group coded as a 0, the beta coefficient describes the change, right? As you move from 0 to 1, what's the change in the outcome? So same interpretation as in the continuous predictor case, only now it literally describes the difference between the groups. As you move from 0 to 1 or from males to females, there's a 1.015 point reduction or a 1.015 difference between the groups. And I've pasted in a little piece of the output from the t-test at the beginning of these slides that shows that the mean difference between these groups is in fact 1.015. So the thing to think about in terms of categorical predictors is it's important to know, very important to know how the groups are coded. You have to know, or you have coded the data yourself so that the reference group, what's called the reference group, is coded as a 0. In this case, I'm using males as the reference group and we're comparing females to males. But the interpretation is the same. As you move from up on x, as you increase on x by every 1 unit increase, and there's only 1 unit to go here, it's the expected change in the outcome variable. So as you move from 0 to 1 or from males to females, the expected change is a reduction of 1.015 points. And here is how the model equations get expressed. It's customary. Well, I'll start at the top. So the first one is the sort of sample-specific expression. So that weird thing on top of sofa is called hat. We often use a hat to express a predicted value. So this says predicted sofa score for any person, right? Sofa hat sub I is equal to 11.29 minus 1.015. And what goes in the parentheses there is, normally that would say the name of the predictor, and we'd be saying for every 1 unit increase in the predictor, there's a corresponding slope change in the outcome. Here we're saying as you go from males to females, there's a reduction of 1.015 points. The second expression is the population model, so it doesn't have the hat, it just says the SOFA score for any individual, because I'm now saying not just in my sample, but for all people to whom I'm capable of generalizing on the basis of my data or the population. Expected SOFA score for any individual in the population is equal to the intercept plus the slope for male, which is the beta 1. Males, remember, are coded as a 0 here. And then plus the thing that differentiates the sample-specific model from the population model is the presence of the sub-I. The second bullet and the third bullet say the same thing. The third bullet just has the regression coefficients plugged into the equation instead of the parameters that represent them, beta 0 being the intercept and beta 1 being the slope. So that's another quick regression example.